All right, welcome. We are in Unit D, our first chapter, and we are doing the last lesson in Unit D, all about nuclear energy. Okay, so here are the outcomes. We are focusing on looking at the environmental impact of nuclear energy, the different types of radiation that is released in nuclear energy. We're going to leave this last few sections for the next part of the lesson, which will be in a separate video. But this lesson covers these pages. Okay, so nuclear reactions and energy comparison. It's really important to understand when we're talking about nuclear energy, we are talking about energy being released that's 1,000 to 1,000,000 times more energy than your typical chemical reaction. So your typical chemical reaction that we've been looking at in this unit are like combustion of methane. Okay, so this is a chemical reaction. And, your typical one, you might have the energy release of 800 kilojoules per mole, something like that. Whereas if you look at nuclear reactions, if you have a nuclear reaction, look at the value you're talking about. You're talking about 1.8 times 10 to the 9 kilojoules. So we're talking about huge magnitudes higher of energy than we ever are talking about with chemical reactions. And that's why we want to harness this energy for creation of electricity and other energy sources, because there's so much coming out during a change. Also, just to note, a phase change, right? So phase change, you studied these a long time ago, probably, grade 9 maybe. Basically, when you're going from a gas to a liquid or a solid to a liquid or something like that, those energy amounts are much less than even a chemical reaction. Okay, so it goes phase change, chemical reaction, then nuclear reaction in the amount of energy released in these different changes. Alrighty, so I like this visual here that shows the energy released through chemical reactions. Okay, so how much you would need to have the equivalent amount in a nuclear reaction. So if we're looking at the like uranium and the heavy water, so you need uranium and you need heavy water to run a nuclear reactor. And say we're looking at that amount, 150 tons of raw uranium. Well, that is going to be the equivalent to the energy here that you're seeing. So the equivalent to 2 million tons of coal or 20,000 rail cars. Okay, and 1.5 million tons of crude oil or 7 super tankers. So all that is equivalent to 8 tractor trailers worth of uranium. So that's the equivalent amount of energy. So you get a lot more energy for a very small amount of mass of substance. All right, so when you hear about nuclear reactions, you probably think and heard about radioactive waste. This is because when we are talking about nuclear reactions, we are talking about radioactive materials. And these materials, when something is radioactive, what does it mean? It means these substances are emitting energy in the form of EMR. And specifically, gamma radiation or alpha, beta, and neutrons, or so they're particles. Okay, so we either have EMR like gamma rays, which we studied last unit, and we know those are very damaging to the human body, and or particles can be released. And we're going to look at these later in the lesson. Alpha, beta, and neutrons can also be released. So these nuclear reactions are said to be ionizing because they can form radiation that those particles that are released, they can actually go and through materials and they can damage living cells. So you probably, when you think of nuclear reactions, you probably think of accidents right off the top of your head. You may have watched a video or a movie or something about some of these different nuclear reactions. One that you've probably heard about is Chernobyl. This was in 1986. It was the most severe nuclear accident in our history. And I'm going to let you read more about this in here, and it's also going to be showing up again in your assignment. Okay, there's another accident that's more in your recent history. You would have all been around for this one in 2011, following that huge earthquake in Japan and the big tsunami that came after that earthquake. It disabled the power supply and it caused mega issues with the nuclear reactors there as well. So again, I'm going to let you read about this. We don't have the name here. Just a second. All right, I had to get the name there. So Fukushima, Japan. This is where the second largest nuclear accident has occurred because of that tsunami. Important to know, a lot of people have died in both of these accidents, less in Japan, but the deaths are also, there's some that are acute, like happen right away, and some of the deaths happen much later on due to the nuclear decay and radiation that is still present in the environment. All right, so now we're going to get into the nitty-gritties of some of the nuclear, the information that we need to know to write a nuclear reaction. So first off, let's take a look at what an isotope is, because we need to understand isotopes before we can understand nuclear reactions. So this may be a review for you from Science 9 or 10. Okay. Radio. So we are going to be representing isotopes with a symbol like this. Okay, so you might see something like that. That would be called carbon-12, and it's the most popular carbon. All right, so popular, when I say popular, I mean it's the most abundant. It's found in nature the most often. So 98.9% of all the carbon we find is carbon-12. Well, what does that mean? Well, this number down at the bottom here, this is your atomic number, and it's the number of protons. Okay, so the number of protons. If you remember, that happens to also be the atomic number on your periodic table, and so that tells you the protons, and you just write it right like that. The number up top here, this is your mass number, okay? And the mass number is, as you can see here, the protons plus the neutrons, P plus N, okay? So they're added together. Then if you just want to find just the neutrons, then you could take the protons and neutrons, subtract the protons, and then you'll end up with your neutrons. All right. So there's another isotope of carbon. So there's carbon-13. So you'll see the atomic number for carbon does not change. So the number of protons is still 6. Never changes. If it changes, if the protons change, then the element symbol, the element is a whole new element. Okay? So 6 protons, but our mass number can change. And that changes because the number of neutrons changes. Remember, this number is the number of protons, down below here, plus neutrons. So the only way that mass number is changing is if the number of neutrons changes. So this carbon-13 has one extra number of neutrons than carbon-12. And you can figure out how many neutrons by doing 13 minus 6, and that gives you your 7 neutrons. Then you have carbon-14, which is the most rare, less frequently found. And you can see again, the atomic number is still 6, so that doesn't change. 6 protons. But if you want to figure out how many neutrons, subtract your mass number and your atomic number, and you'll see there's 8. So there's an additional 2 neutrons compared to carbon-12. All right, so we're going to take a look at some of the different more common isotopes that you will find in your nuclear reaction. So we're going to use nuclear notation, nuclear rotation to express the following isotopes. So the first one's been done for us. So if we see uranium-235, that 235, when we see that, remember when we saw, like this carbon here, we called this carbon-14? Carbon-14. That number here, carbon-14, that is the mass number. Okay, so if you remember mass number from the last slide, it's the number that's shown at the top of the symbol. So you can see uranium-235, you can put the mass number right up at the top. And then to figure out the atomic number, this 92 here, this is coming straight out of the periodic table. You need to look up uranium in the periodic table and find the atomic number. So the atomic number, number of protons, goes right at the bottom of the symbol. And your mass number, which is usually going to be given to you, goes at the top. You can see that uranium here in blue here, it says 238.02. This is not the mass number. This is an average mass number of all the different isotopes of uranium. So uranium, you could have a uranium-238 or a 235, but they told us in the question that it was uranium-235. Okay, but it looks like uranium-238 is probably the most popular because that's the average or the most common. Okay, but doesn't matter. You don't take the mass number from the periodic table. They're always going to give it to you, or you're going to calculate your mass number. Okay, remember mass number here is protons plus neutrons. All right, let's try another question. We have polonium-210. All right, as soon as you see that, well, first off, you're going to have to look up polonium in your data booklet. You have the whole periodic table in your data booklet. So find polonium. You can see its atomic number is 84. That'll help you find it on the periodic table too. All right, so the atomic number is 84. Remember, atomic number is the same thing as the number of protons. Atomic number, where do we put atomic number? The bottom of our symbol. So polonium, doesn't matter what isotope of polonium it is, it's always going to have 84 down below here. We know the mass number, 210. Our mass number here, you can see, our mass number is going at the top. So we put 210 at the top. Let's try another one, uranium-238. I want you to pause the video. Here is your uranium information from your data booklet. You don't even need your data booklet. See if you can put the numbers for the isotope notation in the correct location for uranium. So pause the video, try that, come back. Okay, hopefully you took the 92 because this is our atomic number or the number of protons, right? 92, it's always going to go at the bottom, smaller number at the bottom. Your mass number is always more because it's going to be the protons plus the neutrons, and they give that to us. It's 238. Okay, and then there's another isotope of polonium, PO. The mass number is 218. They give that to us. And the atomic number is still going to be the same, 84 down below. So here's two different types of isotopes of polonium. You can see their atomic numbers are exactly the same. They have to be if they're polonium. It's just the mass numbers that change. If you're not feeling comfortable with this, make sure you do some practice. Go over the practice questions. And these questions on this chart will be of great help to practice as well. I'm just going to do 2 of these and then I'll leave it to you. So we'll do row 2 here. You can see we have oxygen, an isotope of oxygen. If we're going to name this isotope, it's going to be oxygen dash, and we use the mass number to name it. So oxygen 16 is its name for that isotope. Okay, so its mass number is 16, its atomic number is 8. So how many protons are there going to be? There are 8 protons. Our atomic number is the number of protons. How many neutrons are there? Well, remember our mass number here is the protons plus the neutrons together. So we're going to take our 16 and subtract the protons. So we just have our neutrons, which is 8. So there'll be 8 neutrons. All right. I'm going to get you to practice some of these on your own. And the next slide in your slide set has all the answers to these, so you can double check your understanding of this. All right, nuclear decay. So isotopes can become very unstable when their repulsion force is greater than the nuclear force holding them together in the nucleus. Okay, when you have an unstable isotope, it's going to change into another substance, like a whole It could be a whole other isotope. It could be a whole other element even. Okay. And when it does this, it releases energy in the form of radiation and particles. And we're going to study 3 types of radiation here, which we've already looked at gamma rays a little bit, but we're going to look a little bit more detail how we would do an equation with them. We're going to look at beta rays and alpha rays. All of these are super high energy. Remember, way more energy than any kind of chemical reaction. All right, and which one of these has the highest frequency and lowest wavelength? That is our gamma radiation. So that should be something from your last unit. Okay, so gamma radiation, not actually a particle, it's electromagnetic radiation, right? EMR. So that's what it looks like. Beta radiation is actually an electron. Okay, it's actually an electron that's being released. And when we talk about alpha radiation, we're talking about something that has 2 protons and 2 neutrons. And if you look that up, you would see that that is actually just helium. All right, so let's take a look at these, compare these different types of radiation. So if we're talking about alpha radiation, we use this symbol here. So I'll just redraw it so you can see it drawn. There's the symbol for alpha radiation. It's made with 2 protons and 2 neutrons with a net charge of 2 positive. It's not very penetrating, so this can't really go through the body too much. So there's your symbol for it, helium. Okay, it's just a helium atom. All right, and then we have beta radiation. So beta radiation, and this is a high-speed electron, and this is definitely more penetrating. You can see all these different types of radiation on page 8 in your data booklet, so you don't have to memorize these. You're actually given all this information. And this is what an electron looks like in the isotope notation. Okay, it's weird, hey? -1, that's because it has no protons. It's got an electron. So we give that -1. And because this is mass number is protons plus neutrons, it's got none of those, so it's 0 mass number. Gamma radiation looks like that, like a Y. This is, again, the high energy photon. It has no mass, though, and no charge, right? This is very penetrating, the most penetrating, and this is our symbol for it. Again, all these symbols are in your data booklet. All right, so you can use pictures or equations to represent nuclear equations or nuclear reactions. So you could have something like this. So this is uranium-238. You can see the mass number there, 238, so isotope 238. And it's releasing an alpha particle. There's the alpha particle, alpha, so a helium atom. And whatever's left over, it now turns into thurium, I think it is, 234. So it gives away or releases a helium atom and turns into a whole other element. All right, and we can represent that same reaction by this equation here. Uranium-238 over 92. So we have our atomic number and our mass number. Uranium turns into thurium. I got to double check that one. And then a helium or an alpha particle is being released. All right, let's take a look at reaction B. So let's start here. We've got sodium. That should be familiar to you, right? It is releasing or decaying and giving off a beta particle. There's your beta particle, or beta radiation. The sodium then turns into magnesium because it's losing an electron. And it's also, in the picture, we see gamma rays. So normally you would actually have gamma rays then in your equation. That may have gotten cut off. Whoa, that's not a gamma ray. 0, 0, and let's do a Y. There you go. There's a gamma ray. So we should also have gamma ray in our reaction here. All right, so we're going to practice writing some nuclear reactions now. One thing you'll notice is that there's a new term on this page, the nucleons. Okay. The nucleons is just the number of protons and neutrons in the nucleus. So nucleons of potassium is 37. Okay. Now, if you notice and you take a look at all the atomic masses or nucleons, okay, for the reactants. So on the reactant side, we have 37. On the product side, if you total up all the nucleons, you'll see you have 37 as well. They add up to the same number. And you'll see the same thing for the atomic number, 19 on the reactant side, and on the product side, 18 plus 1, 19. Oh, something is wrong here. Somebody has done this incorrectly. All right, so if you will remember from the, actually this is a good teaching point. You'll remember from the last page that actually a beta particle is an electron, and the one was actually negative. Remember that? I'm just going to go back. I'm going to go back so that you can see. Oh, no, don't need to go that far. So you can see here we go. So you can see the electron has a -1 here for its atomic number. So you got to watch that. So in here, it's actually a -1. So this number here has to be 20, because 20 minus 1 will give us 19. So what we're going to do is look on the periodic table for atomic number 20. I want you to see what it is. And looking on the periodic table, atomic number 20 is actually calcium. So this should be calcium. Haha. Okay, so I'll go back and change that on the slide. But this is a good point, because this is exactly what you're going to be doing on the next few slides, figure out what's happening in a nuclear reaction. Okay, so here's an example. Find the missing nucleon in the following nuclear reactions. Okay, so let's figure out what is going to be, what's missing basically. What element, what isotope, what do we got left over here? So we've got Pu, which is plutonium, and then it's giving off a alpha particle, or helium, and something else. So what's it going to be left over with? So we can quickly figure this out, because our atomic numbers here, all our protons have to add up to 94, our reactant side. So 2 plus 92 will give us 94, right? And then on the top here, all of our mass numbers have to add up to 242. So we have 4. So this mass number here has to add up. 4 plus whatever it is gives us 242. So that will be 138. So, but what symbol did we put here? Well, to figure that out, we're going to look up this atomic number on your periodic table. So look up 92. If you pause and find it, you will look and you will see that that is uranium. So uranium has the atomic number of 92. This atomic number is what dictates what symbol and element we're talking about. All right, let's try another one. There it is, 92. All right, find the missing nucleon in the following nuclear reaction. Okay, so it looks like we just have one substance that is decaying into these two substances. We've got sulfur and a beta particle. Now, this is where you got to be careful. So our atomic numbers both have to add up to whatever atomic number over on the left-hand side. So 16 minus 1 gives you 15. Right? So we have to have an atomic number of 15 over here. And then 32 plus 0 is just going to be 32. So how do we figure out the symbol? A symbol is always dictated by the atomic number on the bottom. So look up 15 on your periodic table, pause this, find it, and 15 is phosphorus, P. There you go. Alrighty. So now let's try writing. We're going to give it a word problem. Instead of giving us extra help, we're going to get the whole problem as a word problem. So write the nuclear reaction for the alpha decay of radium-226. Okay, so I want you to pause the video right now and find radium on your periodic table. That's really key. You need to know where radium is. So radium is, I'll just write it up in the corner here. Radium, it has an atomic number of 88. If you didn't find it on your periodic table, it's on page 6 in your data booklet. So we're writing the nuclear equation for the alpha decay of radium. So that means we're starting with radium. And let's write its isotope symbol. We know its atomic number from the periodic table is 88. And we know its mass number from the question is 226. All right, so we have radium, and it is going through alpha decay. Not sure what that is? Let's look in your data booklet for the alpha decay. So look at the top of page 8, and you will see a chart with all the subatomic particles and radiation. And you will see that alpha decay, or an alpha particle, is basically a helium atom. Okay, so if we're going through alpha decay, that means a helium atom is being created. And it only says it's alpha decay, so nothing else is being created. So we need to now know what this other product is. Because the radium doesn't disappear. All these other pieces don't disappear, right? You have all these protons still. So what is our atomic number of this new substance going to be? It's going to be 2 plus whatever it is equals 88. So 88 take away 2 gives us 86 is our new atomic number. And what's our mass number on the top going to be? Our 4 plus whatever the number is here has to equal 226. So we'll take 4 away from 226, so 222. So what symbol do we write, though? This is always the trickiest part. Look at the atomic number. That determines it. So look up 86 on your periodic table, and you will see that we are talking about, where are you, 86? Radon. Rn. Radon. Okay. All right, so that would be done. That would be your nuclear equation for that practice problem. All right, let's try one with beta decay this time. So what is beta decay? Do you remember? If not, go and check on page 8 in your data booklet to see beta decay, or go back a section. Beta decay is just an electron. Right? So that means one of these is being given away or released from polonium, and then it's going to turn into something else. So let's look up polonium. I'm guessing that's a P-O. Where are you, polonium? Number 84. Okay, so polonium. I saw its atomic number is 84, so its number of protons, 84. They give us the mass number, so that is what we write up top. And this is going through beta decay, so we know an electron is being given away. What is the new substance formed that's also being released? All right, so our two atomic numbers have to add up. So -1 plus whatever this number is here have to add up to 84. So that's going to be 85. 85 plus -1 is 84. Okay. On the top here, we have a mass number of 0. So our mass number is still going to be the same, actually. But it's going to be a whole new element because our atomic number has changed to 85. And number 85 is astatine. So our new element is AT. Now, remember, with all of these reactions that we're doing, there's always a ton of energy being released. A lot of energy. Okay. Another practice problem. Oh, this time we have a nuclear reaction for the beta and the gamma decay of cesium-144. Okay, so guess what's going to be released? I want you to pause this at this point. Try and write what you can out to see what you understand and what you don't understand. Okay, and then finish watching the rest of the video. Alrighty, so cesium has an atomic number of 55. So cesium, CS, 55. And we know the mass number is 144. Now, we are told in the question that we're going through beta decay. We know beta is just an electron. And gamma decay is that Y, and the isotope notation is 0, 0. Oh, those are zeros. All right, so we're going to get an electron, and we're going to get some gamma decay, and then we're going to get some other new substance formed. Okay, so let's figure out what it's going to be. The mass number is going to be the same because we have 0 and 0. So 0 plus 144 is going to make both sides have the same mass number totals. And then we need to add -1, 0, and whatever this number all have to add up to 55. So that means this is going to have to be 56 because 56 plus -1 gives us 55. So if we look up 56, that's barium. 56 is the atomic number for barium. All right. So this one is actually a backwards kind of question. We were doing all the other ones where we were finding the product, but this time we are asked to find the original isotope. So it says uranium-235 is a product of alpha decay. So watch these questions. It's a product of alpha decay. So there it is, written as the product. And there's the alpha particle from the alpha decay. And you want to find the original isotope over here. Okay. Same principles exist though. Okay, so our atomic numbers have to add up on both sides. So here these both add up 92 and 90, and 2 is 94. So our atomic number has to add up to 94 on this side. And our mass numbers 2, 3, 5, and 4 have to add up. So that's 9. So 2, 3, 9. Okay, so if we look up 94 on our periodic table, you'll see it's down at the bottom, and that's plutonium, which is Pu. Okay. Alrighty, this is, I think this is the last question. Yep, this is the last question. This is from a diploma practice question. Match the types of radioactive decay numbered below with the appropriate reaction listed to the right. Numbers may be used more than once. Okay, so what you want to look for, those special particles that are on page 8. All those subatomic particles are radiation that's being released. There, you should recognize this by now. As soon as you see helium, that is an alpha particle. All right, alpha particle. So that's a 1. So that's alpha decay, and it's decay because it's on the product side, so it's forming a alpha particle. Here we have a beta particle that's formed. So an electron is a beta particle. Here's another beta particle being formed. So a decay, and then here's another alpha particle, so being formed as a product, so that is alpha decay. That's the end of this lesson. Make sure you ask questions if you don't understand and try those practice questions. You really need to practice nuclear reactions to really see if you understand them.